Welcome back to the deep dive. Today we're doing something a little different. We're zooming in on just one piece of hardware.
That's right. It's the Thor broadcast F-RF-1310-Tx-8mW transmitter.
Because it's a perfect example of the kind of, obsessive precision it takes to move TV signals from copper wires over to light beams.
And that's our mission today. We want to understand how this little box acts as a bridge. It converts the entire TV RF band.
So that's all the channels, everything from 45 to 870 megahertz.
Everything. And it squeezes it all onto a single optical fiber. It's what gives you that modern RF over glass signal, or RFOG.
So we're essentially translating everything that once traveled down a big, bulky coax cable into a beam of light. What's the first hurdle you face with a translation like that?
Well, it's got to be stability and consistency. They use a high linearity DFB laser, which is basically the engine keeping that light beam perfectly stable.
Pushing out 8 milliwatts of power, right?
Yep. But the real intelligence here is the automatic gain control, the AGC.
Okay, so if it's automatic, what happens if the signal coming into the box is, say, too weak or way too strong?
And that's the brilliant part. The AGC just handles it. It can take a huge range of incoming power. We're talking 11 to 29 dBmV.
With no manual setup needed.
Zero. No dials to turn. This automated management means the signal performance stays incredibly flat. It varies by less than, 3/4 of a decibel across that whole frequency range.
So it's built for reliability.
Yeah.
Fewer headaches for the engineers.
Exactly. But let's talk about something unexpected the source material pointed out. Security.
Right. The ability to, and I'm quoting here, create high-security fiber breaks. That sounds pretty dramatic.
It's actually a really clever bit of infrastructure design. See, old-school coaxial cable, it creates a return path.
A vulnerability.
A huge vulnerability. It can leak signals. It allows for unauthorized access. By moving to this optical link and creating these breaks, you essentially just cut off that electrical return path completely.
So it's a one-way street for the signal. Super secure.
It really is. And the quality metrics prove that the signal holds up, even over long distances.
Yeah, you don't just want a stable signal, you need a crystal clear one.
Precisely. We're seeing a carrier-to-noise ratio, a CNR, of over 50 dBs, and that's even at 10 kilometers of fiber.
And a CNR over 50 is like the gold standard for broadcast video, right?
It's the benchmark. Then you have to worry about all those channels interfering with each other.
That's where CTB and CSO come in, composite triple beat and composite second order.
Correct. They're just measures of distortion. And the specs here, CTB below negative 63 dB and CSO below negative 57 dB, are superb.
In plain English, that means what? A perfect picture.
A virtually flawless high-def picture. It doesn't matter how many channels you're pushing through or how far it has to go.
That level of fidelity means the installation has to be just as precise. The input is just standard coax, but the output.
The optical output. That's where the obsessive precision really shows. It uses a 1310-millimeter wavelength, and, this is critical, it demands an SKPC connector.
APC, angle polished connector. Why is that tiny 8-degree angle so important?
Because we are fighting the smallest possible enemy, light reflections. A flat connector, like a standard SCPC, reflects a tiny amount of light straight back into the laser.
And that little reflection can just ruin everything.
It can completely destroy the signal integrity we were just talking about. The angle on the SCAPC ensures any reflected light gets diverted away, harmlessly.
Which means if you're installing this and your fiber has one of those flat connectors, you can't just plug it in.
No, absolutely not. You have to use an optical jumper to make that conversion to the SCPC angle. If you don't, you lose all the high-performance benefits of the system.
It really shows how this kind of technical translation depends on getting the physical details exactly right.
And that precision engine is what allows for really complex setups, not just simple point-to-point runs. You can build out massive networks with splitters and couplers.
So this deep dive has really shown us that moving broadcast signals from electricity to light isn't just about speed. It's about maintaining this near-perfect fidelity against something as tiny as a reflection.
The whole system is engineered to handle every variable you can imagine, all for the sake of reliability.
So what does this all mean for you? Given this need for security features like fiber breaks and the absolute requirement for angle-polished connectors to maintain quality, what unforeseen challenges or even vulnerabilities might pop up as our critical infrastructure keeps shifting from simple, forgiving copper wire to this kind of ultra-precise light transmission? That's something to explore on your own. Until next time.